We're back. Okay, so we want to know the probability that we have one success, specifically where the 5 is appearing when we are rolling a die. We want the discrete random variable to have the value of 1 because that's the number of successes. And we say that that is equal to n choose k times the probability to the power of k times 1 minus p to the probability of n minus k. All right, so we have n equals 15. K is my one success. The probability, what is the probability? Well, it's the probability of a 5 on a die. Okay, so I'm only considering the 5 to be deemed a success. So there's one 5 on a die where there are 6 possible outcomes. So the p-value is 1 out of 6. All right, so n choose k where n is 15. 15 choose 1 times the probability of 1 over 6 times the k value of 1. 1 minus 1 6 to the probability of, or to the power of n minus k, where it's n is 15 and k is 1. Okay, so let's see if we can do this here. All right. So what is that equal to? So it's equal to 15 factorial over 15 minus 1 factorial times 1 factorial times 1 over 6 to the power of 1, and then 1 minus 1 6 is 5 6 to the power of 15 minus 1, which is 14. Okay, so 15 factorial over 15 minus 1 factorial is 14 factorial times 1 factorial times 1 over 6 to the power of 1 and 5 over 6 to the power of 14. Okay, so when we type this in, so we have 15 factorial divided by, now that's scientific notation, so it's this number times 10 to the power of 12, okay, because my calculator screen isn't large enough to show the multiple numbers of digits, okay, multiple digits. Okay, so then it's divided by 14 factorial, and then it's divided by 1 factorial is 15. And you say, I don't understand that. Well, 15 factorial is almost identical to 14 factorial. The only difference is that this numerator has a 15 times 14 times 13 times 12 times 11, etc. And this is a denominator of 14 times 13 times 12. And then they cancel out, and the only thing that's left in the numerator is the 15. So that's the 15 equals 15 times 1 over 6 to the power of 1. So that'll just convert. So 0.16 repeated. And then if I don't want to convert this as a fraction myself, I just go bracket 5 divided by 16, close my bracket. It converts the decimal, the fraction to a decimal, and then I go to y to the x, which is 14, and then equals. So that number there is 0.0778865, blah, blah, blah. I don't clear the screen, right? And then I go times 0.1666666, as many times as I want, times 15 equals 0.194716413, and we'll round that. I think the calculator answers in the back of the book are going to the nearest fifth decimal place. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. So underline the 5th digit, look to the 6th digit. 6 is 5 or greater, so it bumps up the 1 that I've underlined to a 2. Okay, so that is the probability of exactly 0.15 when die is rolled 15 times. Okay? Okay, a die is rolled 7 times. Determine the probability that 2 3s appear. Okay, so the number of trials is 7, so n is 7. My number of successes is 2. I'm happy with the 3 appearing twice, so my k value is 2. Right? I'm going to use the probability of the discrete random variable taking on value of 2, where that's n choose k, times the probability to the power of k times 1 minus the probability to the power of n minus k. So I'm going to sub in a value of n where it's 7 trials. My k value is 2. And my probability that I get, my p, which is my probability of getting a 3 on a die. Notice I'm not looking at 2. 2's been already taken care of by the k value, okay? So what's the likelihood of getting a 3 on a die? Well, that's one outcome that I'm successful with, which is the 3, out of a total of 6 possible outcomes on a die. So the probability is 1 out of 6. Subbing that in, so I get 7 trials, 7 choose 2 times the probability of 1 6 to the power of k, which is 2, times 1 minus 1 over 6 to the probability of 7 minus 2. So that's the same as 7 factorial over 7 minus 2 factorial times 2 factorial, 1 over 6 squared, and then 1 minus 1 6 is 5 6 to the power of 7 minus 2, which is 5. Okay? So equals 7 factorial over 7 minus 2, which is 5 factorial, times 2 factorial, times 1 over 6 to the power of 2, and then 5 over 6 to the power of 5. Another thing you can do, when adding these exponents, they should always equal the number of trials, so 2 plus 5 is 7, and then these two numbers, they should always equal 1 whole. 1 6 plus 5 6 is 6 6, which is 1 whole. So that's another way to make sure you're doing your math correctly. Okay, so 7 factorial divided by 5 factorial. When I press division, okay, it'll get me the answer of these two numbers, okay, and then I'm going to divide that by the 2 factorial. So 21 times 1 over 6 squared, so I go bracket 1 divided by 6, close the bracket, it'll convert my decimal or my fraction to a decimal, and then y to the 2 or y to the x, which is 2, equals 0.027 with 7 repeated, and then 5 over 6 bracket 5 divided by 6, it'll change my my fraction to a decimal, to the power of 5 equals 0.4018777572, and then all of these numbers multiply together. I do not clear the screen for this number here, times 0.027, continue to press the button, times 21 is equal to 0.234428 blah blah blah. We'll round to the nearest fifth decimal place. 1 2 3 4 5, that's a 2, but the 8 is 5 or more, so it bumps up the 2 to a 3. So 0.23443 is the probability of exactly 2 3s when the die is rolled 7 times. Okay? All right. What about a coin toss? Now again, these can all be represented by a tree diagram, but obviously drawing multiple branches to represent 100 coin flips is ridiculous, and that's why we're using our formula, right? So it's the same as, you know, when you had to add 2 10 times, 2 plus 2 plus 2 plus 2, and then eventually in elementary school you went, oh, that's 2 groups of 10 or 10 groups of 2, and then you use multiplication. Okay, this is the same thing, right? All right, so if a coin is tossed 100 times, that means our n value is 100 trials. I want to find exactly the probability of getting 40 heads, and that in this case is the k value. Okay, notice that heads is not being assigned a value per se. Okay, it's the number of successes, and that's really what we transition to do. So we're not taking the value of the heads, but we're associating the value of the heads with the number of successes. Okay, so we can use, like before, the probability of the discrete random variable taking on the value of 40. So it means that we've got 40 opportunities to be successful, okay, is equal to n choose k times the probability to the power of k times 1 minus the probability to the power of n minus k. And we're subbing in now the n value of 100 trials. The k value, we're talking about 40 successes. Okay, and then the probability. Well, the probability is the probability of getting a head on a coin toss. Well, that's the same as 1 is my number of successful outcomes, because I can only get a success if I have a coin flip resulting in head, out of the 2 possible outcomes being a coin flip of a head or a tail. Okay, so that's my p-value. All right, so n choose k, so that is 40. Choose, oops, not 40. My number of trials is 100. 100. Choose a 40 times p, which is 1/2, to the power of k, which is 40. 1 minus 1/2 to the power of n minus k, which is 100, minus 40. Okay, so we have 100 factorial divided by 100 minus 40 factorial times 40 factorial times 1 over 2 to the power of 40, and then 1 minus 1/2 is 1/2, and 100 minus 40 is 60. All right, so what is our combination going to be? So it's 100 factorial over 60 factorial times 40 factorial times 1/2 to the power of 40 times 1/2 to the power of 60. All right, so 100 factorial doesn't give me a possibility to do that, so I'm limited, right? Now let's see if I can work around it. Possibly I can do the following. I could possibly say that for 100, factorial is 100 times 99 times 98 times 97 times blah 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 times 60 times 59. And I should really put another number here, so I'll do that. So all the way down to 61 times 60 times 59 times blah, 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 times 1. Now, you already realize that this is getting a little bit ridiculous, right? And then what I would have to do is I would have to evaluate what 60 factorial is. So it's 60 times 59 times 58 times blah, 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 times 1. And then it would be times 40 factorial would be 40 times 39 times 38 times blah, 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 times 1. We already realize that this is absolutely ridiculous, okay? And then this would be to the 1 over 2 to the 40, and this would be 1 over 2 to the 60. Okay, are we going to do that? We'd say, okay, n equals 100 represents a lot of trials, right? Why not use another method? Okay? Question. Okay, that's where, therefore, we'll use the normal approximation of the binomial distribution in day 2 tomorrow. Right? So what did I say at the beginning? I said that this Z table represents probabilities that represent multiple trials, maybe trials of 100, maybe trials of 500, large sample sizes, and that's where the Z table comes in for these questions in 5.4. Okay, let's look at this next one. E, if a coin is tossed 100 times, we still have this problem, okay? Now I want at least 40 heads. That means that the K value has to be 40, it has to be 41, it has to be 42, it has to be all the way up to K equals 100, because that's the maximum number of trials. Okay? Since n equals 100, n, K greater than or equal to 40 up to 100 are a lot of successes. Okay, therefore, we'll use tomorrow's normal approximation of the binomial distribution. Stay tuned. Meanwhile, try these. These are all very manageable using the methods of A, B, C, and D.